Alright, next up on our list of alkene reactions is one that basically is a little odd. And that is the reaction with hydrogen. Now, in and of itself, this will absolutely never happen. In and of itself, drawn the way I have it right this second, this would have an activation energy the size of the Empire State Building. It's just not going to work. There's no driving force for it. There's no reason for it to ever occur. This is a reaction that absolutely requires a catalyst to bring down the activation energy to get it to work. Usually this is palladium, sometimes platinum, and at that point we actually get addition of two hydrogens, preferentially syn on the same face to each other, like so. Now, there are a lot of problems here. First, palladium and platinum, the two metals that are generally used here, are enormously expensive. Okay, problem number one. But, as I said, it's catalytic. So very much like the osmium we talked about earlier, we're not using very much of it. In fact, tremendously small amounts of this actually still works because it's a very efficient catalytic process. But second, this, unlike the osmium case, is what we call heterogeneous catalysis, meaning the catalyst is not in solution with everything else. It is not dissolved. It is a solid sitting at the bottom of the flask or being agitated around by a stir bar. We generally disperse it on something like graphite or carbon, so you'll sometimes see it written as something like this. This is just a way of making it easier for us to handle more than anything else. It disperses the expensive palladium over a wider surface area of carbon and lets us get a better catalytic surface out of it. So first, it is stereoselective anyway, very much syn addition. That is actually not quite perfect, but it's close, which tells us that it's not exactly a synchronous addition, otherwise it can't possibly give you any anti, but it does not give you much, and we'll talk about why that is in a moment. But second, that heterogeneous thing is a little strange, because that means we've got something happening not in solution, and that the dynamics of coming in and out of solution for our reagent may actually speed up or slow down this reaction because we're going to have to leave solution to get to the catalyst. So let's talk about how this is thought to work. First, we're going to have basically a surface, and sometimes just drawn like this, with the idea that this is my metal. So, and when I bring hydrogen in the presence of that, what I get is a split out of the hydrogens from each other. And that's why I said this has a massively high activation energy most of the time, is because it involves actually separating the H's from each other. Now, that is not normal. There's basically very little that will do that, other than combustion will separate the H's and H2 from each other. So this is a very odd reaction. Useful, but still odd. Now, there's a couple of problems with what happens next. Is my alkene reacting with one of those H's? Is it getting drawn into the metal and then handed off to those H's? That's debatable. There are cases where the actual pi bond of something like an alkene is coordinated like so. So the fact that those exist suggests that the palladium can interact directly with the pi orbitals. So it means we got some odd things going on here. Generally, how it's written is like this. If I bring in that alkene, and for simplicity, I'm just going to draw an easy one here just so that I can actually get it in place. So I'll just draw tetramethyl. What we generally see happen is drawn like this, that we've ended up with one H added to the alkene, and so I have something like this, where I now have H that's been added here to that left carbon, and the right one is still is actually frequently drawn as being attached to the metal surface now, where the other H still resides. So then the metal does a bit of a handoff job and we end up letting go of the alkene completely. And I'm drawing a bad conformation here just so it's clear that everything's added to the same face. So we end up with something like this, where now my alkene has picked up those two hydrogens and it's gone. There are some issues with this explanation, but they're a little bit more advanced than they're worth bothering with at this point. You'll see them in later courses for those of you that continue with organic, but this is a bit of an oversimplification. The metal interaction here is a little bit more complicated than we're giving it credit for. But essentially, if you've watched old Three Stooges films, this is kind of comparable to something like Curly and Larry being slammed together, with Moe grabbing both of them by the head and smacking them together. That's kind of what this handoff step here looks like, is that you've kind of got those two being held by very likely separate metal atoms, but then they just get sort of pushed together in such a way that it happens faster than the rotation of the center bond. If that center bond rotated, we'd start seeing non-syn stereochemistry. That's not actually what we see very often. We do see a very tiny amount of it sometimes, which tells us that this is not perfectly synchronous. Well, it doesn't, drawing it out like this, we can tell it's not, but there are some suggestions that it's not a perfectly synchronous reaction. So, again, if we drew that with something that's actually substituted, and I chose the same example again, but we're going to see basically entirely the syn addition. So we're looking at essentially all of the hydrogens being added to exactly the same face with very tiny amounts otherwise. Typical solvents for this reaction, usually when I've seen it done, it's ethanol. Relatively cheap, easy to come by, except when you need hand sanitizers. So it is an almost foolproof reaction, except for this part up here. It does require a little bit of special care to handle hydrogen gas. This reaction usually requires a piece of equipment called a hydrogenator. What it is a stainless steel flask with bolt-on tops and a pressure, so you can put more than 1 atmosphere of hydrogen gas in it. And then it has this fairly primitive-looking agitator that just basically shakes it like like one of those baby rockers that you see, the auto rockers for kids. It just basically takes this flask and jars it back and forth over time, because remember, this is heterogeneous. So it needs to be consistently agitated to mix properly. Homogeneous reactions don't have to have that problem, but this has to be continuously agitated. Depending on the reaction, some reactions, not with alkenes, but some reactions we'll talk about later on in the course, you can use hydrogen gas at atmospheric pressure, at which point basically all you need is a balloon, similar to what you would use for a helium balloon for a birthday party, and just stick it over the reaction, and that atmospheric distribution of hydrogen be enough. For alkenes and for alkynes, that's not enough. You need to raise the pressure a bit. So you need special equipment for that. This, obviously, if you're going to raise the pressure, you're not doing it in glass, unless you happen to like shrapnel being pulled out of your face, assuming you survive it. So it has to be done in special equipment. This is not trivial, but it is not dangerous once you have the gear to do it with. It is not. It's not particularly difficult, but it's just not something that you can walk downstairs into any lab and be able to do. All right. So again, we could use palladium. We could use platinum. There are some complexes that are homogeneous, that dissolve a little bit better. But these are the ones that are still most commonly used, because they're essentially very cheap and, aside from the need for special equipment, very nearly foolproof.